Greetings, differential equation scholars, and welcome to this video on using Laplace transformations to help solve initial value problems. In this video today, we're going to take a look at the solution to a second-order initial value problem from the vantage point of Laplace transforms. In our video today, we're going to be taking a look at the initial value problem that you see at the left. This initial value problem states that the solution function y must satisfy the non-homogeneous differential equation y double prime plus 3y prime minus 4y is equal to the cosine of t plus the sine of t. And we're going to insist that that solution function y has to satisfy the initial conditions that the function evaluated at 0 is 0, and the function's derivative evaluated at 0 has a value of 1. Now, we already know some important things about the solution to this. Indeed, we could solve it using techniques that we already know. For example, we know that the homogeneous equation that's associated with it has an auxiliary equation of m squared plus 3m minus 4 equal to 0. So because that auxiliary equation has solutions of m equal to 1 and m equal to minus 4, we therefore know that we expect a complementary function of the form c1 times e to the minus 4t plus c2 times e to the t to solve the related homogeneous equation. As far as the non-homogeneous portion goes, we can predict that that solution will be of the form a cosine of t plus b sine of t. And so that overall, the solution to this initial value problem must take the form complementary function plus particular solution. It's going to have this particular form. Now that we know that it has that particular form, the question is, since we know we're expecting a solution of the form some constant times e to the minus 4t plus another constant times e to the t plus a third constant times the cosine of t plus a fourth constant times the sine of t, the question is, what are those constants? Now, we could find those constants using our older techniques, but in this video, we're going to take a look at how we can find the solution using our newer lenses of the Laplace transform. I would invite you as an exercise, when we're finished, to go back and check for practice that you can get the same solutions by applying the constraints of the initial conditions and the fact that the particular solution must satisfy the differential equation. But in this video here, we're going to concentrate on the Laplace transform approach. As a first important review, remember that if capital Y of S is used as a notation for the Laplace transform of the solution function y, in a previous video, we reviewed some important derivative theorems. One core theorem says that the Laplace transform of the derivative of y is equal to s times the Laplace transform of y minus the function y evaluated at 0. We might call that our first derivative theorem. But if we take that a step further, since a second derivative is a derivative of a derivative, we can apply that formula twice in succession, and we would obtain the idea that the Laplace transform of the second derivative of a function y is s squared times the Laplace transform of y minus s times y evaluated at 0 minus the value of the derivative evaluated at 0. Pay attention to those two theorems. We're going to be using them now and applying them to help solve our initial value problem. If we take that differential equation and we apply the Laplace transform to both sides of it, that will give us the following result. The Laplace transform of the left side equals the Laplace transform of the right side. But then we can apply the linearity of the Laplace transformation to say that the Laplace transform of the second derivative of the solution plus 3 times the Laplace transform of the first derivative minus 4 times the Laplace transform of the solution equals the transform of the cosine of t plus the transform of the sine of t. As we look at that equation there, we see that we can make substitutions for all of those transforms. Now, first, on the right-hand side, let's use what we know about the transforms of the trigonometric functions. We remember that the transform of the cosine of t is s over s squared plus 1, and the transform of the sine of t is 1 over s squared plus 1. We substitute those in on the right-hand side. Now, on the left-hand side, we've got the transform of a couple of derivatives, the Laplace transform of the second derivative and the Laplace transform of the first derivative. So we can apply our derivative theorems from just a moment ago to help see what that expression would be. The Laplace transform for the second derivative, we substitute in s squared times the transform of y minus s times y of 0 minus y prime of 0, and we replace in the middle the Laplace transform of y prime with s times the Laplace transform of y minus y of 0. And of course, we can replace the Laplace transform of y with capital Y of s, which is our notation. So now we have applied the transform to all of the pieces on both sides. We notice that on the left-hand side, there are several pieces that involve our initial conditions. There are two pieces that involve y evaluated at 0. We see those in red at the left. But remember that our initial condition said that y of 0 was 0. So those pieces are just going to be eliminated and vanish from the left-hand side. There is also one piece involving y prime of 0, and we can substitute in 1 for that. Doing so is going to make the left-hand side become considerably simpler. It'll just become s squared times the transform of y minus 1 plus 3 times s times the transform of y minus 4 times the transform of y. And that will equal the expressions on the right-hand side. Now we notice that on the left-hand side, most of those terms involve capital Y of s, the transform of our solution. There is one term, minus 1 on the left, that does not. What we'll do is we'll collect all the terms involving capital Y of s on the left, and we'll move that term that doesn't to the other side. That now gives us that s squared plus 3s minus 4 times the transform of y equals s over s squared plus 1 over s squared plus 1 plus 1. Now, as for those fractions on the right-hand side, we can do some algebra to combine them. First of all, we note that the first two fractions already have a common denominator, so they can be combined to give s plus 1 over s squared plus 1. But the other term, the 1, could be written as s squared plus 1 over s squared plus 1, so that we can combine all of the terms together. When we do so, we'll see that the right-hand side becomes the rational expression s squared plus s plus 2 divided by s squared plus 1. The left-hand side, we see, could have its trinomial factored. S squared plus 3s minus 4 does factor into s plus 4 times s minus 1. And after realizing that, we see that we now can get an expression for the Laplace transform of our solution. We found that whatever our solution is, its Laplace transform is the rational function s squared plus s plus 2 divided by s squared plus 1 times s plus 4 times s minus 1. We don't have our solution yet, but we're very close because we do have the transform of the solution. What that means, now that we've found the transform of the solution, is that our solution will, of course, be the inverse transform of that. So now our problem of finding the solution to this initial value problem has become one of finding an inverse Laplace transformation. Whatever function is the inverse transform of that rational function is the solution to our IVP. Now that rational expression, of course, can be broken down using partial fractions. Our theory of partial fractions tells us that that rational expression should be able to be written as as plus b over s squared plus 1, because that piece has an irreducible quadratic, plus c over s plus 4, a linear term, plus d over s minus 1. Partial fractions tells us that we can write that rational expression in that form, that sum of simpler fractions. Our solution will be the inverse transform of those three fractions. Now, before we find the constants a, b, c, and d that are necessary to make that true, let's take note of the following important realization. First, when we look at the first fraction on the right-hand side in the partial fraction decomposition, as over s squared plus 1 plus b over s squared plus 1. Well, those pieces are, of course, the Laplace transform of a times the cosine of t plus b times the sine of t. So that means that that first piece on the right-hand side, when we inverse transform it, will give a contribution of a cosine t plus b sine of t to the solution to our initial value problem. And recall, we were expecting just such pieces to be there. Now, what else will we have? Let's look at the linear terms. The second piece on the right-hand side is c over s plus 4. We're going to also find its inverse transform eventually. But we know, remember, that c times e to the minus 4t has a Laplace transform of c over s plus 4, exactly the fraction we see on the right. So that means that that second fraction, when we inverse transform it, will give us a contribution of c times e to the minus 4t, which again, remember, was also expected to be part of our solution. And finally, the last piece. We know that the Laplace transform of d times e to the t is d over s minus 1, precisely the third fraction that we have. And so that means that we will also expect a contribution of d times e to the t as part of our solution function coming from that third piece of the partial fraction decomposition. There we have it. We see that this approach of taking inverse Laplace transforms of this partial fraction decomposition is in fact going to give us exactly the form of the solution that we knew from earlier we were expecting to find. So now let's find those constants, a, b, c, and d. Remains to do some algebra work to find those out. If we multiply both sides of that equation, of that equality, by the denominator, clearing the denominator tells us that as plus b times s plus 4 times s minus 1 plus c times s squared plus 1 times s minus 1 plus d times s squared plus 1 times s plus 4 must equal the numerator of the left-hand side. That must equal s squared plus s plus 2. Now, that equation has a variety of ways that we can approach it to find the constants a, b, c, and d. One approach that you may recall is to make strategic substitutions. Of course, the values s equal to minus 4 and s equal to 1 will make many of the terms on the left-hand side of that equation disappear. For example, if I take s equal to minus 4, the first and the third terms on the left side disappear, leaving us with the equation that c times 17 times minus 5 equals 16 times negative 16 minus 4 plus 2. And that means that negative 85c equals 14, or that c equals minus 14 over 85. We've now found one of our constants. We can easily find another one by substituting in s equal to 1. Taking s equal to 1 makes both of the first two terms on the left-hand side disappear and leaves us only with d times 2 times 5 equal to 1 plus 1 plus 2. In other words, 10d is equal to 4, meaning that d ultimately is 4/10 or 2/5. we've already found the constants C and D that are going to be, in the end, the coefficients of our exponential terms in our solution. But what about the A and the B, those coefficients of our sine and cosine term? Well, while there are no more substitutions that will eliminate terms so quickly, there are some other substitutions that give us very simple equations. For example, if we take s equal to 0, taking s equal to 0 on the left-hand side will then dictate that b times 4 times minus 1 plus c times 1 times minus 1 plus d times 1 times 4 must equal 2. And that gives us a very simple linear equation involving just b, c, and d. There's no a in that equation. And since we already know the values of c and d, we can substitute in the values of negative 14/85 and 2/5 that we found previously. When I substitute them in, I'll find that negative 4b must equal 4/17 after we do the arithmetic. And that means that b then is negative 1/17. Aha! Well, we now have 3 of our values. We know b, c, and d. Only one constant a remains unknown. Again, a substitution now will help us to find the remaining constant. We could really take s to be anything we wanted at this point. I've chosen s equal to 2. Taking s equal to 2 gives us that 2a plus b plus times 6 times 1 plus c times 5 times 1 plus d times 5 times 6 must equal 4 plus 2 plus 2. In other words, we see that 12a plus 6b plus 5c plus 30d must equal 8. That's a linear equation involving our 4 unknowns, and we already know the values of b, c, and d. I can substitute in those values of b equal to negative 1/17, c equal to negative 14/85, and d equal to 2/5. And we're going to find, after we make those substitutions, that it turns out that 12a must equal 20/17 minus 4, or negative 48/17. But if 12a is negative 48/17, dividing by 12 tells us that a is negative 4/17. And now we have the coefficient of the cosine term of our solution. Having found all of our constants, we now know precisely the solution to the initial value problem. We know a and b, negative 4/17 and negative 1/17. Those are going to be the coefficients of our cosine and sine terms in the solution. We know c and d, negative 14/85 and 2/5. Those are going to be the coefficients of our exponential terms in our solution. What is the transform of our solution? Remember that we had said we knew that the transform of our solution were these 4 constants times s over s squared plus 1, and 1 over s squared plus 1, 1 over s plus 4, and 1 over s minus 1. This is the transform of our solution in all of its glory. But we know that the inverse transform of s over s squared plus 1 is the cosine of t. We know the inverse transform of 1 over s squared plus 1 is the sine of t. We know the inverse transform of 1 over s plus 4 is e to the minus 4t. And we know the inverse transform of 1 over s minus 1 is e to the t. So by using linearity, we now have our full solution to the initial value problem. Taking the inverse transform of those 4 pieces, we're going to get negative 4/17 times the cosine of t, minus 1/17 times the sine of t, minus 14/85 times e to the minus 4t, plus 2/5 times e to the t. Notice, of course, that this again follows exactly the format that we had predicted at the very beginning. But even if we hadn't known any of the earlier theory from chapter 4, By knowing the theory of Laplace transforms, how to find the Laplace transform, and how to find inverse transforms. With the help of partial fractions and some algebra, we have found the solution to our second order initial value problem. A very interesting and useful approach. I hope you found this video to be useful as you work on furthering your understanding of Laplace transforms and their use.